All right. Hi, everyone, and welcome to this talk about our paper. Is this correct? Let's check. And this is joint work with Omri Ben-Eliezer, Elchanan Mossel, and Madhu Sudan. All right, so before I actually discuss what's going to appear in the paper, let me start with the story. Perhaps some of you know it. So in 1904, Henri Lebesgue proved the following theorem, that a projection of any measurable set is still measurable. Okay, this is a result in measure theory from the beginning of the last century. Now, according to Google Scholar, this is somewhat of an influential paper. It has around 3 citations. And a small but non-zero fraction of those citations come prior to the year 1917. Now, the reason why I mentioned the year 1917 is because in that year, something interesting happened. And this is the story where Suslin read Lebesgue's paper and found the following counterexample, that there exists a projection of a measurable set which is not measurable. In other words, Suslin found a mistake in Lebesgue's paper. Okay, this turned out to have a somewhat of a happy ending because it led to the birth of the field of descriptive set theory and to many other results. But one question remains, what happened with all of those papers which relied on Lebesgue's paper prior to 1917? In a sense, they might have used a wrong result, and it could be that Lebesgue's mistake propagated forward. Okay, so quantifying the effects of such mistake is somehow what we aim to do in this work. And let me now open with a meta question, which will be the main focus for us today. Is, given such a mistake in a paper or in any knowledge producing system, what can we do to guarantee that the effects of a single mistake or a single error do not propagate forward? Or well, not that they don't propagate forward, but we limit their effects. Okay, in order to answer this question in a more precise sense, what we do, we define a model for the process of accumulating knowledge. So this can be the scientific process in which you write paper which build upon other papers. This can be more related to software development, where you write a library which builds upon other libraries, and so on. And any process in which you accumulate knowledge. And what we want from our knowledge to represent is to have new units of knowledge added to it over time, and each new unit of knowledge will need to build upon previous existing units. But our model will also have the ability to introduce error to each new unit of model. So some new units of model will be erroneous, okay? But errors can be checked and rectified. So once there is a checking procedure which checks for errors in the model, and once an error is found out, it can be removed from the process. Okay, so it's a sort of a growth and destruction model between the introduced knowledge and the removed errors. And what we focus on is the structural properties of the model. And for example, the question is, do errors propagate forever? Okay, so what I'll do now, I'll explain the model in detail. And after that, I'll hint about some of the results we obtained for this model. So let's start with an ideal situation. Okay, ideally, we would like to store knowledge as a directed acyclic graph. Okay, each node represents a unit of knowledge, say a paper. Edges represent units of knowledge building or inheriting from one another. For example, when a paper cites another paper. It's a directed acyclic graph because there should be no cycles in the citation, but every node can cite multiple other papers. Now, in order for us to define such a model, we would need to define a proper model of clustering, right? Because the set of papers, the single paper sites, usually have some similarity between them. And well, this might lead to a somewhat untractable analysis. So we decided for now to consider a simplified notion and represent knowledge as a tree. Okay, so every paper cites one major paper instead of several. So, okay, in our knowledge, in our process, knowledge is represented as a tree. We call it the knowledge tree. And a node represents a single unit of knowledge, and edges represent the relation of building upon existing knowledge. Now, every node has two types of labels. A hidden label, which is the objective truth written in that paper or in that knowledge. Those two labels are conditionally true for true knowledge and conditionally false for false knowledge. But initially, those states are unknown. Okay, only the public states are known, which is what the public knows. Okay, so those are the proclaimed true states, for short PT, and the proclaimed false state, PF. Now, a node can be wrong in two cases. Either it is conditionally false, objectively the knowledge inside it is wrong, or it builds upon a wrong unit. Okay, so a node is false in those two cases, and in other case, it holds true knowledge, which means that all ancestors up to the root of the tree are conditionally true. But this is a hidden state, of course. So this is the structural properties of the model. Now I'll explain the dynamics. Okay, there are three processes going on. One is the process of accumulating knowledge, adding new knowledge, units of knowledge. Then there's the process of introducing errors to the model. And then there's the process of removing errors from the model. So let's start with accumulating knowledge. All right, so it's an iterative model. At each time t, we have a knowledge tree at time t and its associated labels, like the tree we have here at the bottom. To add a new unit of knowledge, we generate a new node, and we choose a random parent from among all of the proclaimed true parents. Okay, proclaimed false parents are essentially out of the game. You are not going to cite a paper which is known to be wrong. How do you choose a random parent? This is done according to the preferential attachment model. In brief, the more children you have, and here we only consider proclaimed true children, okay, the more influential you are, and the more likely you are to spawn new knowledge. Okay, so basically the higher the degree of a node is, the more likely it is to be the parent of a new node. Now, what are the labels of each given new node? The public node is always proclaimed true. Okay, it's assumed to be true until proven otherwise. So that was the process of accumulating knowledge. Now, what is the process of introducing error or of injecting errors? So recall, every node also has a hidden state of the objective truth inside it. Either it is conditionally false or conditionally true. So for every new node, we throw a biased coin, we introduce a parameter epsilon, and with probability epsilon, the new node will be conditionally false. Otherwise, it's conditionally true. So in some sense, this parameter epsilon is the proportion of truth, the proportion of errors in our process. Okay, so for example, in this tree, the new node chose the root as its parent, but turned out to be a false node. It contains some mistake in it. Okay, it is conditionally false. Now, what is the process in which we check for errors? So every time a new node is added to the tree, we throw another biased coin, this time with parameter p. And this is the probability that you are checking the knowledge you inherit from. Okay? So with probability p, the node checks its ancestors, and with probability 1 minus p, it does nothing. Now, what does it mean to check? A node checks its ancestors up the tree. It ascends the tree upwards. We introduce another parameter k, which is the number of levels a node goes upwards. And if at any point when it traverses the path up the tree, it finds either a proclaimed false node, which was publicly false, or a conditionally false node, which contains some mistake, then the entire path from the node to the wrong parent, to the wrong ancestor, changes to proclaimed false. Okay, the entire the path becomes publicly false. Essentially, it is removed from the tree. Right. So to summarize what we define for the process, knowledge is represented by a tree. Knowledge is added according to the preferential attachment model. More influential nodes tend to become even more influential. Errors are introduced randomly when new knowledge is created. Checks are performed, again, randomly when new knowledge is introduced. And error correction is done by proclaiming faulty nodes to be false. So that was our model. And with the three parameters we introduced, epsilon, the proportion of errors, P, the proportion of nodes being checked, and K, the depth of each check, we call or define this model the epsilon PK CKP. Okay, CKP stands for cumulative knowledge process. So now let me discuss a bit about our results. So let's go back to the original meta question we had and make precise sense of it in our model. Right? So we ask, can we guarantee that the effects caused by a single error do not propagate? So what are the effects caused by a single error in our model? So an error is represented by a conditionally false node, as the hidden label CF, and the propagation or everything which is caused by that error is all the false nodes which resides in the subtree rooted at that node. Now, what would it mean to not allow the errors to propagate or to eliminate error? And this is the following observation. If at any point in the process, all descendants of a faulty node become proclaimed false, then the tree is essentially eliminated, right? No other nodes can join that subtree, and it is frozen in time. So that mistake cannot propagate forward. Okay, so that leads us to the following definition. If in our model, we look at any conditionally false node and we look at the subtree rooted at that node, if we can say that with probability 1, almost surely everything there becomes proclaimed false, then we will say that the error effects in this model are completely eliminated. Right? Otherwise, there is some positive probability that the errors will propagate forever up to time infinity. And then we say that the error effects survive with positive probability. And then now our meta questions become, for which set of parameters, epsilon, P, and K, okay, checking probability, error probability, and depth of checks, can we ensure that the error effects are completely eliminated? Okay, so let's state our first result now. And our first result applies to the role of the depth. It turns out that the depth plays an essential role. Okay, our first result shows that depth matters and that shallow checks will never suffice to eliminate the error effects. Okay, so formally, if K is 2, if you are only going to check 2 levels upwards each time, then it doesn't matter what proportion of knowledge you are going to check for any non-trivial P, the error effects will survive with positive probability. Okay, so there is a positive probability for some mistake to propagate forever. And the idea of the proof is rather simple. Okay, we couple the CKP, the cumulative knowledge process, with the branching process. And because the checks are so shallow, we are able to show that if you look at a false node and you look what happens at the subtree rooted at that node by the time it is proclaimed false, well, we show that effectively it generates many new components beneath it. Okay, so by using a branching process argument, well, it just shows that there is some positive probability of this tree growing up to time infinity. Right, and the conclusion is very simple. If you want to guarantee that the error effects are completely eliminated, you cannot have checks which are too shallow. If you're going to write a paper and you want to ensure that no mistakes propagate too much, it is better to check not only the paper you cite and the paper they cite, but a few levels upwards as well. Now, it turns out that this is a unique property of very shallow checks, because our next result, it identifies a phase transition for non-shallow checks with respect to the checking parameter P. Okay, so formally for any k, for any depth of checks which is at least 4, and any non-trivial epsilon, okay, any non-trivial proportion of errors, there exists some threshold, let's call it P naught, such that if the proportion of checks, if P is larger than P naught, then we can ensure that errors are completely eliminated in the CKP. And otherwise, if P, the proportion of checks, is smaller than that P naught, then the error effects may survive with positive probability. And again, the conclusion is, if the checking procedure is not too shallow, if you are going to check at least 4 level upward, there is some minimal amount of effort you can put in the model to guarantee the elimination of error effects. And now, the proof of this theorem is a bit involved with many details. I'll just explain a bit about what we do. And basically, the idea is to reduce everything to a martingale, or rather a sub-martingale and super-martingale analysis. We define several observable of the process, which we track a long time, and we analyze the dynamics, and we show that in some regime of parameters, those observable increase in expectation or decrease in expectation, and this allows us to say something about the long-term dynamics. And some examples of those observables are the number of leaves. So for example, if we can show that the number of leaves in expectation goes to 0, then the tree must be eliminated. Okay. Another example is the distribution of depth, at least for proclaimed true nodes. Okay, how many proclaimed true nodes do you have at each level, and then we weight it accordingly so that we can make some sense of it. Now, one thing we do is we not only look at this question of whether errors survive forever or are completely eliminated, but we can also use those observables to make a somewhat more refined observation and results about the process. Okay, so one thing we also look at is, how does the tree look like when the error effect do survive? So you have some false tree which goes on forever, but we managed to identify parameters in which it is not too large. It does not occupy any linear proportion out of the entire tree. So, and we also control the size of it, actually. Okay, and another thing we look at when the error effect is completely eliminated, you will always have some false node, simply because the tree keeps generating false nodes by this parameter epsilon. Because you can ask when error effects are completely eliminated, how many false nodes do you actually have? What is the proportion of false nodes? And we show that, again, there is a set of parameters in which there are no false nodes above the noise level, above that parameter epsilon. Those are in brief our results. Let me just say a bit about future direction. So the two theorems, the two phase transition I showed or I discussed with respect to depth, they show that k equals 2, depth equals 2 is special, and then you have a phase transition with respect to p when k is at least 4. But somehow our analysis misses the case of what happens when you are only checking 3 level ups. So that is interesting to check. Another thing which is interesting to find out is what is the exact value of P naught in the phase transition. Okay, what is the minimal amount of effort you need to invest in order to ensure that errors are completely eliminated? Our result is somewhat existential and we give bounds, but we do not know the exact value of P naught. And maybe a more general future direction is to consider more general models, as we discussed before. Okay, instead of trees, maybe we can consider directed acyclic graphs, and this will require us to extend the preferential attachment model to directed acyclic graph by also taking care of this clustering of knowledge. We want a new node to choose a subset of parents which share some similarity. And that's it for today. Thank you for listening.